Well, today's speaker is somebody that I've known since before I even was a graduate student. I think he was a graduate student. I think I was between college and grad school, but we were at the same place at the same time in the mid 1970s, which was the Harvard Smithsonian Center for Astrophysics. And I was working between college and grad school, and Sten was a grad student at Harvard. He has gone on to have a really amazing career at NASA. He has studied the cosmic infrared background. He's done a lot of stuff with space weather. My personal favorite thing that he did, of course, is an education thing, which is that Sten single-handedly made up this thing called Space Math at NASA and developed just an amazing amount of math-oriented resources for teachers and students. He's the author of over 20 books for the general public. Some of the pictures of some of them are on the slide. He's written numerous articles for popular astronomy magazines. He's been on TV and on radio, and he also has blogs at astronomycafe.net. So today he's here to tell us about the heliophysics big year. As you know, lots of cool stuff is about to happen with the sun, or maybe not so cool. Maybe it's hot stuff that's about to happen to the sun. So with that, I think I'll stop sharing again. And yes, I'll stop sharing and I will turn the sharing over to our speaker.
Let's see, I think you have my presentation and you have to step through the pages.
No, I don't personally have it. You may have sent it to Ariana.
I did.
Yeah, and unfortunately now she's not here.
Okay.
So do you have it yourself that you can share? Or do you
yeah, I do. The only problem is we have problems putting this on the display mode, PowerPoint presentation mode. But I could certainly give it a try here.
Okay, or maybe also just email it to me just in case. Try it first, maybe.
It's pretty big.
Okay,
yeah, that's the problem. All right.
Well, let's just try it first then.
Okay, so let me try the share screen first, and we'll try to get it going here. And if I put it in slideshow.
Okay, so far so good.
Okay, can you see this?
Yep.
Oh, does it come up a full screen?
Yes, for me it does.
Oh my gosh. Oh, that's
Looks
amazing.
Great, Sten.
Wow, because it didn't do that before. Okay, well, first of all, Lynn, thank you so much for having me give a talk. And for the rest of you that are listening, I'm on the East Coast, and you know, I'm 3 hours ahead of you in time, so I get to see the future 3 hours before you guys do. Well, that's not strictly true, but on the clock, it looks pretty impressive. Anyway, so the heliophysics big year is an idea that NASA has had for quite a while. Back in 2012, we had something called the Year of the Solar System. And what we did there is to offer a bunch of resources to teachers and students that kind of focused on NASA planetary missions and the solar system and the properties of the planets, things like that. It was a lot of fun. A lot of people participated in this, and so we thought it was a real big success. Since then, we've had a couple of eclipses. A big one in 2017 was quite impressive that we enjoyed. This year, we're doing the heliophysics big year. And the idea here, hopefully I can step through this. Can you see the next slide okay?
Yeah.
All right. It starts with the annular eclipse this October. So that's a nice way to start this year. The middle of this year is the total solar eclipse in April, which is going to be really cool. The nice thing about both of these is that they're both visible from the United States. And actually the paths of these eclipses, where you can see them completely, crosses in basically the northwest corner of Texas. So it's a kind of a double magic area geographically if you happen to live anywhere there. The end of this heliophysics big year is going to be the Parker Solar Probe. It's been orbiting the sun and getting closer and closer with each orbit. And December 2024, it'll be at its first perihelion passage about 5 million miles from the sun. So it's going to get a really, really, really good view of the outer corona, and the place, hopefully, where a lot of the solar wind gets its start. And the solar wind is an important feature of the sun's outer atmosphere, so we're really interested in how that all works. But the thing is that, you know, these details, we call it heliophysics, which is sort of the study of how the sun interacts with the Earth and the planets, not just through its wonderful light and radiation, but also through, you know, things like what's called the solar wind, which is an outflow of particles from the sun, and through various flares and things like that, which can really wreak havoc with our satellites and other things. So heliophysics, you know, sort of is this, it's like the Prego spaghetti sauce. You know, anything you can think of that has to do with the sun and how it interacts, it's in there. If it's heliophysics or helioseismology or solar wind or flare studies or magnetic reconnection, it's in there. But we don't like to say all those words together, so we just call it heliophysics. Okay. Well, it's going to kick off, of course, this October with the annular eclipse. And the idea is that each one of these months has a kind of a general theme. Dr. Nikki Fox at NASA headquarters came up with this idea a few years ago. And, you know, each of these months is going to have a theme that is going to engage the public and also engage students and teachers and maybe even your pets. Whatever is touched by the sun, either through light and heat or whatever, you know, should find something interesting to do during these months, during these thematic periods. Well, anyway, the annular eclipse not only is going to be observed by people on the path of the eclipse, but we have a number of interesting citizen science projects, which are really kind of cool, that are going to go on at the same time. One really neat one is called the Dynamic Eclipse Broadcasting Initiative. This is a bunch of ham radio operators who are going to try to communicate with each other across the path of totality. And the idea is that the reception that they get will depend on the properties of the ionosphere, which will change during the time that the eclipse and the sun is blocked by the moon. And the ionosphere is temporarily in shadow. So that's going to be kind of cool. We'll get to see what the ionosphere does and how rapidly it does it. And that's a citizen science project. For the next month, November, we're going to celebrate all of the wonderful NASA missions, satellites that study the sun. And we have an actual armada of missions at this point, 14 or 15 spacecraft that are all investigating some aspect of the sun and the way it interacts with the Earth. Also, this is the month where the atmospheric waves experiment is going to be launched. This is an experiment that looks at the upper atmosphere of the Earth. Mainly, it's looking at gravity waves, which are produced by the atmosphere, and also is going to use air glow measurements to see just how space weather and the sun interacts with the upper atmosphere. So we're going to learn a lot about the details by having this mission actually looking at some of the properties of the ionosphere. In December, coming up really quick, this is a big month for citizen science celebration. During the total solar eclipse and the current one coming up, there are a number of citizen science projects that are going on that are going to look at various aspects of eclipses and aurora and things like that. And these are all projects that you can participate in yourself. You don't have to be an Einstein with a big brain or a PhD. You can do this yourself if you're an interested amateur or hobbyist, and have a lot of fun meeting people that are kind of like-minded and really interested in these subjects. Then in January, well, the sun touches everything. If it doesn't touch it with its particles, it touches it with its radiation. And the radiation from the sun is what drives our weather patterns day to day, and also long term drives our climate. Sunlight coming into the atmosphere, heats up the gas and produces various things that go on. What we're going to do with one mission called TSIS-1 is we're going to continue to measure very accurately just how much solar energy comes into the Earth. And this is really important if you're creating long-term climate models. You have to get this number right, and you have to know how it changes over a long term, like a decade or so, in order to get your forecasts as accurate as you possibly can. So, we can celebrate that mission, but we can also think in terms of how the sun basically is important for growing plants, which is our agriculture and everything else that we rely on that has to do with sunlight, including getting our own energy, which is a new thing. February, nominally, it's a reflection on the sun in fashion. Well, I couldn't find a whole lot of examples of fashion that is key to the sun, but clearly what you wear in the winter is different than what you wear in the summer. So, the sun influences your fashion choices that way in a fairly obvious way. An interesting and fun thing is that the solar wind that comes out of the sun, it actually forms a kind of a skirt-like ballerina skirt that waves throughout the solar system, like a flapping kind of a skirt. And the Earth goes in and out of this thing every 4 or 5 months in its orbit. The Parker Solar Probe is actually going to be studying this as part of the solar wind and figuring out, exactly the details of how this is produced. But I just thought it was kind of fun that, there is, something about fashion in the way the solar wind behaves as this big floppy skirt that flops throughout the solar system in a kind of a funny way. Let's see, March, well, okay. Ways of experiencing the sun that have, nothing obvious to do with things, but here we have the case of a mission called Themis, which is examining just how aurora are produced. And so that's kind of a tip of the hat to the Themis mission, which has been in operation for 866 weeks or so. And it's, a way of experiencing the sun that doesn't involve just the radiation, but essentially other daily influences on us, like there's things like season-affected disorder, where, if you don't get enough sunlight in the winter, some people get sort of depressed. I kind of suffer from that a little bit. So sunlight is important throughout the year for human behavior and other things. So this is a March time to reflect on how the sun affects us in other ways that are not necessarily physical. In April, of course, we have the big solar eclipse, which we'll be able to participate in. In fact, there are going to be something like 160 million people in the US that are going to be able to see some aspect of this eclipse, whether as a partial eclipse or, if they're lucky, on the path of totality itself. So this is a real large event for people. And I hope that some or all of you are going to be able to see at least a partial solar eclipse, weather permitting, from where you're located. I know I'm going to be looking at it in Washington, D.C. So we'll see how that works. May would be a nice time to talk about visual art related to the sun and heliophysics. Here is an artist, Lena Dania, who was part of a program as an artist, professional artist, to paint various aspects of the sun. And she selected the Parker Solar Probe. And if you click on this link and go to the YouTube website, you can actually see her from start to finish paint this beautiful painting. So the sun as an element of art, is something that's been going on for, it's been going on for thousands of years, from the time of the ancient Egyptians, up to the present. There's always been something having to do with the sun. in many of the artworks from, the great civilizations. In June, we have performance art. Well, that was a hard one for me to kind of figure out, what to do on that subject, because the idea was something about performance in either music or dance that had to do with the sun. Well, I remember Carly Simon in "You're So Vain" singing about the total eclipse of the sun in Nova Scotia, and it turns out that there was one in 1975. So that's a connection with with a real event in music. And I also thought a little bit more crazily about the fact that some of the orbits that these satellites do, can get absolutely complicated and bizarre, like this one from IC3. This image shows the absolutely bizarre orbit that this spacecraft took in studying the Earth's magnetic field and the particles, and then becoming, progressing out to become a comet mission, and then finally to go and look at Comet Halley later on in its life. So spacecraft orbits can look like really complicated gravitational dances, and most of them are a lot simpler than this. But some of them can be really quite amazing when you plot them out. Physical and mental health, well, the sun is important in that, as I mentioned about seasonal affective disorder. But I'm thinking, like, how many steps would it take to walk to the sun? I mean, that was sort of one of the defining elements of this theme, from Nikki Fox. And I thought, well, yeah, that wouldn't be very plausible for me. I mean, I don't really walk that far. I'm a biker. I do mountain biking on the C&O Canal. But then I thought, well, Voyager 1 is now the most distant operating spacecraft that we have after 47 years. It's way out there, 15 billion miles from the Earth. And then I did a really quick mental calculation. That turns out to be about 40 trillion steps. Okay, so, if you want to go that distance and think that steps is important for health, well, definitely Voyager 1 is a very healthy spacecraft at 40 trillion steps. We have back to school. Well, that can be a variety of things that have to do with the sun. One of the things that's really cool is that the International Space Station views our Earth. It views aurora, and it also views the Milky Way at the same time from its platform. So you can photograph literally all three of these things in the same scene. I'm not sure if you can see this. I'm going to try to run this video, which was taken by the International Space Station. I hope you can see this. This is real imagery. I mean, you can see city lights, thunderstorms, you can see the Milky Way, and then you can see the faint red glow of what's called air glow. So, back to school could be a time to reflect on the role of our Earth in space and the things that influence it, and how we can now view the Earth from a very, very unique perspective in the universe, actually from outer space. You might recall that some time ago, the Voyager spacecraft took images of our Earth as seen from beyond the orbit of Saturn. And all you see with Earth is this little blue dot, which is what Carl Sagan called the little blue ball. Mostly it's blue because of the oceans, but that's it. I mean, that's Earth in space, a very precious and very, very amazing place, but it's only one spot in an entire universe. So it might be nice to think about that as you're going back to school. September could be a time to think about environment and sustainability. Of course, the sun is a powerful source of electromagnetic radiation. Spacecraft use that to run their electrical systems. They use solar panels to collect the sunlight and convert it into electricity. And in terms of what we're doing on the Earth now, is that we're starting to replace some of these annoying fossil fuels with solar energy. And this little graphic shows that we're actually coming a long way. in providing clean energy using the sunlight as we see it today. The curious thing is that the gas and the coal are stored sunlight from millions of years ago. So in a sense, even our fossil fuels are frozen sunlight that we're liberating by basically burning them. But solar panels are much cleaner. You're not burning anything except perhaps in their manufacture. And they provide clean energy just the way satellites do in space. So we're very quickly turning to that as a green and sustainable way of lighting our civilization. In October 2024, we can think about the sunspot cycle. And we're sort of rising up towards the peak. And by then, we'll probably be very close to the peak of the current sunspot cycle. And as an activity, you can consider, if you have the opportunity, to use a sun spotter or a telescope with a proper eyepiece. You can actually observe sunspots. You can count how many that you see there every day, and track sunspots as they move across the face of the sun as the sun rotates. So sunspots can be a kind of an interesting key to learning about the sun and its cycles, which are important in a number of areas. In November, we have what we're going to call the bonus science month. We don't know what kind of discoveries we're going to be talking about in November a year from now, but we certainly know that artificial intelligence and machine learning are likely to be a big part of that. This particular artwork was created by an AI program. I have no idea how it did it. I'm sure the creators don't have any idea how they did it because it's all done internally in a black box through networks that are trained. And so nobody understands how AI works. But here we can see a piece of artwork that it came up with that is not too bad. I mean, I think a high school student could easily produce something as interesting as this. But neat thing about AI is that it helps us solve the problem of having literally terabytes of data from these satellite networks that we have, and trying to find very efficiently and quickly patterns within the data that we can then interpret in terms of testing theories or creating new hypotheses and theories from them. AI is far more efficient in doing that than humans are. Once a human trains an AI network, how to do pattern recognition in a particular database, it's phenomenally effective. And it can even apply that to archive data that we already have, that we thought we had basically exhausted for any scientific utility. So, I mean, that's 2024, about AI. Then finally, yay, we get to December, Parker Solar Probe. Orbit number 22, it gets within about 4 million miles of the sun. And hopefully it's going to help us figure out some aspect of how the solar wind is actually produced, because the solar wind comes from a region that's about at that distance or a little bit closer to the sun, but we'll sort of be at the hairy edge of the solar wind's birthplace. So who knows what we're going to find out? We expect to find out some really cool things, but only time will tell. And I think if you want to find some interesting things about heliophysics big year, you can sort of go and look at the website at NASA. You can have a look at Nikki Fox's wonderful YouTube video. And let your mind wander a little bit. I mean, the theme is the sun, and reflect on all the different ways that the sun affects you, affects the way you live, and be very creative about coming up with ideas that you might want to celebrate each month. If nothing else, try creating a PowerPoint like this, as I had to do last week, knowing virtually nothing about the subject, but then having to come up with some interesting graphics and themes. I mean, that's what the creative process is all about. So in a sense, the big heliophysics year is a celebration of human creativity. And, the sun is as good a theme as anything else that you can select. And that's about it. I'm looking forward to your questions at this point.
Well, thank you very much. That's more than a year, though. The heliophysics big year, maybe it's big because it's longer than a year, right?
Well, yeah, it's a year on Jupiter, I guess, or something, you know. That's 13 months. That's close. It's a Jupiter year.
So we had some questions in the chat. Let me, I think probably the one that could be best answered is, could you just explain a little bit more about what is the ionosphere and where is the ionosphere? Because I don't think that's familiar to everybody.
Well, if any of you ever watched the Broadway show Cats, you heard about the heaviside layer. It's basically another name for the ionosphere, which is a layer of charged atmosphere. It's about 100 miles or so up above our heads. It's used for ground-based communication because it acts like a kind of a mirror for radio waves, so you can bounce long and shortwave signals all around the world, you know, using the ionosphere as a kind of a mirror. The ionosphere is controlled by ultraviolet and X-rays that come from the sun, which produces the ionization up there. At night, of course, the sunlight goes away, so there's less of it. But in the daytime, there's quite a bit of it, and the ionosphere is denser and thicker, and so you know you can sort of scatter waves much more efficiently. But it's basically an ionosphere because it consists of charged particles, basically oxygen and hydrogen atoms that are charged.
Okay, so now we'll call on people that have raised their hands. So Sid, I think you're up. You want to unmute and ask your question?
Yeah, the ionosphere thing was my question. And I was also going to ask, what kind of radiation does the sun emit that causes the particles to be charged? But that got answered too.
Right. Mainly the charging comes from the X-rays. The sun always produces X-rays, and these can come from active regions on the face of the sun, from sunspots, from flares. The X-rays, they enter the upper atmosphere, the thermosphere is it called, and eventually they're absorbed because they are absorbed by atoms like oxygen and hydrogen and the major constituents of the Earth's atmosphere. When this happens, they often knock off electrons, and so you wind up with the kind of a charged gas up there that consists of neutral atoms, which haven't been hit by the X-rays yet, and charged atoms, which have been hit, and then electrons, which are sort of ejected from the atoms that get hit by the X-rays. And so you wind up with a plasma. It's called a plasma, an ionized gas. And so long as the sun continues to produce X-rays, you will continue to have this ionization up there. Too much of the ionization is a bad thing because there's a layer just below the ionosphere, which the more X-rays you give it, the more it tends to absorb the radio waves that go through it to get reflected. And so then you wind up with these short wave outages whenever you have a solar flare. So yeah, it's a complicated layer, and the sun kind of modulates how this layer behaves by controlling the amount of X-rays and ultraviolet light that essentially reach the Earth.
Huh, all right.
Could you say something about 2025 and the solar maximum and what we're expecting to have happen?
Well, this is cycle number 25 in the counting that we do. And quite frankly, 15 years ago, there were some astronomers that had predicted that we wouldn't even have a 25th cycle, that we were going to go into a 100-year period where we would have no sunspot cycles based on some indicators that they were using theoretically. But as it turned out, this cycle has turned out to be very active. In fact, it's more active than the previous one, and it looks very much like the one before this, which was cycle number 23. So we're expecting a lot of coronal mass ejections, a lot of solar flares, a lot of radio outages. Our satellites are much more robust today than they were 20 years ago. So we're not likely to have very many satellite outages like we did in the late 1990s. So, for the most part, you really shouldn't notice a whole lot. I'm not quite sure I would want to be an astronaut in the International Space Station because some of these coronal mass ejections produce radiation storms that are really intense. And the astronauts literally have to run for cover even inside the space station, which is a hard thing to do because you don't have very far you can run. So that's going to be a problem. But for you down here, we'll notice that there might be some really brilliant auroras every few months during sunspot maximum. And that'll be sort of the event for us.
Well, I know that one of the more formative events in my life was during the solar maximum in 1979, when all the satellites started falling out of the sky, including one that I was working on for my PhD thesis,
Oh my
which
gosh.
was SAS3. And of course, the Skylab, which was the space station before the International Space Station, also fell down that year.
Well, the SpaceX Starlink satellites, they have a real problem with space weather and solar flares, because whenever you have a solar flare, it heats up the upper atmosphere, which causes it to expand out. And if you happen to be a satellite, all of a sudden you'll see more friction, and that'll cause your orbit to decay. And that's exactly what happened to several dozen Starlink satellites a year ago. As they were just launched, they were just ejected from their rocket, and all of a sudden they started re-entering the atmosphere almost immediately because the friction was so high. So it's a real problem.
Okay, well, I think we're sort of out of time for questions. So if you could stop the share and then maybe copy those two links and put them in the chat so people could click on them.